hopefully this will be a fun talk. It's some stuff David and I have been doing over the last couple of months, and I really like it. It might tend on the abstract end, but hopefully I'll make it somewhat relatable, and please ask questions as usual. Okay, so let's start with some motivation. And the motivation is just to kind of consider products in the monoidal category of sets. So you have the category of sets. One is a one-element set, and times is the usual Cartesian product of sets. And then, given some set, we get some things for free. So, because we have products, we have a diagonal map, which, right, delta A, so this is a map from A to A times A, and what does it do? You give me an element, and I give you back twice. Okay. And then the other thing we get for free, just by the nature of this category, is a terminal map for every object. So if you give me, so it's a map, it's a function from the set A to the one element set, and if you give me an element of A, I give you back the unique element. I just throw it away and give you back the unique element of 1. Right? So this is all very nice. We might draw these things. I might draw this like this, where the y is representing copies of A. So I take one copy of A and I duplicate it. And I might draw this like this, where I just take my A and I throw it out, and nothing comes out on the other end. Okay? So we have these structures, and in fact they obey some more laws. So these obey things like if I get an element and I copy it, and I copy the second copy, I get 3 elements, they're all the same. So that's the same as copying your element and then copying the first element. So now I have 3 elements, but in all cases the result is the same. Right? So it obeys that. It obeys if I sort of copy something and then throw out one of the copies, it's the same as just not doing anything. And it didn't really matter which copy I threw out. And there's also the fact that if I copy something and then I switch things around, let me do it like this. If I copy something and then I switch those copies around, well, it's the same as just copying it and not switching around, because those two things were the same. Okay? So we have this category, and every object in this category is equipped with this thing obeying these things. Equipped with these structures obeying these equations. And these, we call these equations the commutative comonoid equations. And so the upshot is that every object in set is equipped with a commutative comonoid. So this is a nice sort of fun playground to play with. We can, when we're drawing diagrams, we have our standard diagrams where we can draw sort of functions, and we can just say, now we have these additional icons where we're allowed to duplicate things and so on. But there's a tiny bit more structure we need to talk about for it to sort of be really nice to play with, and that's some compatibility. So, example string diagram. And this compatibility sort of says, if you remember, in this sort of string diagram world for working in this category, we can say, I can take some object A and some object B, and I sort of represent these by lines, saying I have my copy of A, and it sort of continues to exist through time. But I can also say, well, I have this object A times B. And these two things are to be considered equal, right? Having a copy of A and a copy of B is the same as having, being of in A times B, right? A pair. But if we're to use these icons now, I might say I want a copy of A and I have these things for every object A, I can split it and get 2 copies of A, and for every object B, I can split it and get those things twice. But similarly, if I have A in this object A times B, I have a diagonal of that as well. And so for this to be a nice world to operate in, we would want these things to be equal. Because, well, they're the natural things you construct from these things, and you just, I don't know, you might make that mistake. You might assume these things are equal. And if they weren't, then you would run into trouble. So this story is about this very simple setting where we have some category, and every object in that category is equipped with some algebraic structure, and also it obeys the appropriate properties that reflect this structure, that it's compatible somehow with laying your diagrams, with a monoidal product, so doing your diagrams. And so this seems like a really important simple story, and people have been working in this setting for a long time. These structures come up like a hypergraph category is a category C, where every object is equipped with a special commuted Frobenius monoid, and so on. Or if you're doing probability theory, often you do want some commuted comonoid obeying some properties on every object, and this helps you reason about, I guess, duplicating and marginalizing somehow, like sort of sharing variables. So there's one more element to add to the picture where I won't sort of write out in this motivational section, but in fact there's this fact that I'm dealing with set with the product, and so this has certain universal categorical properties. And so working in this picture, there's this notion of being homomorphic with respect to these structures, and that in fact allows you to recover notions of universality, but in a completely diagrammatic way. So we'll see that as we go forward. Okay, so there are a couple of elements. There's a symmetric monoidal category, we can draw diagrams, and then I say that every object should be equipped with some algebraic structure. So I should at least remind you what I mean, or some way of thinking about generic algebraic structures. And so we've seen props before, but I'll remind you what they are, and in particular the perspective of them as some notion of algebraic, or more precisely symmetric monoidal theory. Okay, the definition of a prop is simple. Once you know what a symmetric monoidal category is, a prop is a strict, symmetric, strict monoidal category such that where the monoid of objects is the natural numbers under addition. Okay, so again, sort of the picture here is a symmetric monoidal category is one of these worlds where you can do two-dimensional reasoning. It's strict means that so if you remember, you have a tensor product that is defined in a binary way, but this means when you start doing ternary things, you have options, you have this option, or you have this option, right? So 2 ways to define the product of 3 things in a symmetric monoidal category. And so in general, it's sort of enough to say that they're isomorphic in a coherent way and to work with these, and this gives you a symmetric monoidal category, but in a strict one we make them equal. And then the objects themselves form directly in monoid under this tensor product, and we can talk about that monoid and demand that it just be the freest monoid. It's just generated by 1, right? We add 1 to itself as many times as we like, and there are no relationships between them. Okay, so some examples of props then. To give examples then is quite easy as a symmetric monoidal category because we don't need to say what the objects are, we just need to say what the morphisms are. So here's an example, the prop of bijections. So in this example, again my objects are just natural numbers, so m and n, and the morphisms between m and n are just the bijections. be slightly more formal, I'm going to underline them and remind you that when I write M underlined, I mean just some generic set with M elements. So some people like to call those elements 0 through to M minus 1. Some other people like to call them 1 through to M. But anyway, so that's this set. Sorry, that's the set of morphisms between M and N. You'll notice that if M and N are not equal to each other, then this set is empty. So an example morphism, so the morphisms are just permutations. So here's a morphism from 3 to 3. It goes like, you have 3 elements, another 3 elements, and we just commute them. Okay. These things can be composed as you compose permutations. You swap some things around, and you swap them around some more. Okay. These string diagrams are slightly different from those string diagrams, and the point is that they're essentially, somehow you interpret these in that world and they become the same. But that's just something to be aware of and to keep in your mind. Another nice example of a prop is the prop that I'm going to call, I'm going to call D for duality. Cob was for cobordisms, but D is probably a better name. So here the hum sets are sort of pairings. I'm sorry. Yeah, I'll call it pairings in M plus N. What I mean by this is that if I want to talk about a morphism from, say, 3 to 5, it's crucial that they add up to an even number. Then what I can do, a morphism is just taking these 8 elements and grouping them into pairs. So I'm going to pair these two, and I'm going to pair these two, and I'm going to pair these two and these two. And so you can also view this sort of in this very trivial manifoldy way as a one manifold with sort of boundary.
Are you allowing circles?
Am I allowing circles? I'm not. I'm quotienting by them.
Okay, you're going to kill all your scalars later.
Hmm?
You're going to kill all your scalars later.
Yeah, so the composition here is you sort of, you can do it diagrammatically.
I just meant in Hilb or something.
Pairings like that. Oh wait, you were worried about a circle being created. So you can do that and kill that.
Okay, I thought you were going to use it for Hilb later.
Yeah, that's a good point. That's annoying. Okay, I'm going to call it sort of the free thing generated by this. So these are our morphisms. We can have a bunch of these things and we can have some circles. That does become relevant later. Okay. It's another example of a prop. They all seem very combinatorial and trivial so far. One more is the prop F. Oh, actually no. I wanted to say that I wanted to just talk about, so I've said sort of a prop we should think of as some sort of algebraic theory. And so in what sense can you think of these things as algebraic theories? One way is to sort of, one way is to take these props and understand them in terms of generators and relations, and look at presentations. And that might help sort of you see sort of more a theory like the theory of a monoid or something, theory of a group inside these pictures. So this is just simply the theory of duality, and that's what D stands for. And so you have these generators, so D is generated as a prop by sort of these two morphisms, which I'm going to call cup from 0 to 2 and cap from 2 to 0, subject to the equations that say if you cup and then you cap, it's equal to the identity, and if you go around the other way, it's also equal. So let's see if I do this thing. So, So in some sense, this is the algebraic structure where we're given these two operations with these laws that they have to obey. And then you can sort of generate this whole world of them, every possible thing you can syntactically do with these generators subject to these equations, and you get this picture here, where the morphisms are sort of these pairings.
Is that just saying you have an isomorphism? Like is that, or does you have an invertible?
It's more like an
A function
junction.
from that to set would be a invert of function with an inverse. Or
Would it be a function of this?
You don't mean an isomorphism between m and n, do you? Right?
a 0 and 2 and 2 to 0 with a.
So it's not the case that sort of 0, like this is equal to the identity, if that's what you're, that sounds a bit more like what you're saying.
I was just curious if that meant you had like f from A to B and g from B to A, such
Mhm.
that f and g are inverse, and that's the algebraic theory there.
It has a bit of a sense. I see where you're getting that from, but I don't think that's exactly it. It's a bit more helpful to think of these as somehow sort of generically the theory of an adjunction, but that's not quite right either. So, well, we can discuss after. And one last prop I want to talk about is just the prop f, and f is standing for finite sets, I guess. So here, or functions, that's also what it stands for. So the Hom set is simply functions from m to n. And so, i.e., I don't know, a simple example, a morphism from 3 to 4 says that a function says, give me an input element, which output element does it go to? So I might draw it like that or something. And there's a picture of a function. We can compose these. What's nice is that this prop has a really nice, is a really familiar algebraic structure as well. So this prop is, maybe I should say presented by rather than, so f is presented by these sort of generators, which I'm going to call, so something from mu from 2 to 1, I'm just going to draw it like this, and then another thing which I'm going to call eta from 0 to 1, which I'm going to draw like this. Okay, so this prop f, which is the prop of functions, is generated by these two morphisms, subject to with equations, which look like this. I.e., they're exactly the dual. They're exactly the dual of these commutative comonoid equations. That is, f is somehow the prop for, well, f is the prop for monoids. This is an associativity law, these are unitality laws, and this is a commutativity law. And it turns out that this gives a presentation of the proper functions. So what does that mean sort of theory-wise? Well, there's a nice theorem that says if we pick any symmetric monoidal category, then we have an equivalence between, so I'm writing SMF for strong monoidal functors from this prop F into C with commutative monoids in C. So you could specialize to set if C equals set times this example up here, if that makes you slightly more comfortable. But the basic idea is if I have a strong monoidal functor from F to C, how do I get a monoid out? Well, this maps to the monoid. A monoid needs an object in C, so you can pull out that object by just figuring out where 1, the generating object of F, being a prop, goes. And then to get what else do we need? We need a unit in our commutative monoid, but we have this sort of map eta in F, which goes from 0 to 1, so we can get a map from M eta, which I guess, do I have color? No, which I'll annotate down here. So this is a map from, well, it's a map from M of the monoidal unit 0 to M of 1, but because it's a strong monoidal functor, this is isomorphic to the monoidal unit I and C. So that thing is of the right type. And similarly, well, approximately up to isomorphism, which I'll fudge through here. And similarly, if we need a multiplication, we can do M of mu. Right, so that this, if you believe those equations hold, which you might believe for functions, they're easy to sort of check, then you can see that this is a commutative monoid in C. And similarly, if you will go back the other way, if you want to go back the other way, you start with a monoid, a commutative monoid, so an object A, together with a unit map and a multiplication in C. How do you get out a symmetric monoidal functor from this prop F? Well, you can define this functor Fa, which goes from F to C, and you send the natural number m, so on objects, you take a natural number and you map it to a to the m to the power, and if you take the generator eta, so this function from 0 to 1, then you can map it to eta a, which you've got as a morphism from sort of 0 from the unit to a, which is the image of 1. And you can map mu to mu of a. So this somehow defines a bijection. This is a bijection between these two sets, and in fact an equivalence of categories. Actually, sorry, I shouldn't say bijection, I'm going to say equivalence of category. It's slightly weaker than, well, that's the right place to live. So, in particular, the takeaway then is I was sort of talking about props because I want to define what it means. So we want to say a sentence like every object in our category is equipped with an algebraic structure. So I need to sort of define some notion of algebraic structure in the abstract to equip my objects in my category with. And so what this is saying is that I can, for example, take F to represent the algebraic structure of monoids, and so somehow this prop F encapsulates abstractly the essence of the notion of a monoid. And to sort of instantiate that essence inside a category C to actually get a monoid, that's the same as taking some appropriate sort of functor from F to C.
What do you mean appropriate sort of? Just
well, symmetric, strong monoidal functor, strong symmetric monoidal functor. Because by theory here, I mean sort of symmetric monoidal theory. Okay, so sorry for the camera work, but I guess to summarize what I was just saying, the idea here is that sort of a prop we think of as containing the essence of some algebraic structure. Whether it be monoids or duality or this is just sort of permutationness, objectness. Okay, so now I have that ingredient. Now I can actually get to this main definition of supply, which captures this idea that every object in our category is equipped in an appropriate way with some algebraic structure. The definition. Right. P is a prop, C is a symmetric monoidal category. Then a supply S of P in C, so of the algebraic structure in the world that we want to work in, is simply for each object in C, a strong symmetric monoidal functor S sub C from P to C. So this picture should look a lot like this picture here, where for every object in C, I get a functor from my algebraic structure, sort of P or P to C, right? Does that make it clear? Well, so it obeys some properties. But what we see so far is that for all objects, we get an instance of algebraic structure P. And what does this make it? How do we make this nice? How do we make this cohere? Well, firstly, this functor must sort of equip the particular object C with this algebraic structure P. So I want to say that S sub C of M is equal to C to the nth tensor power. And so this looks a lot like this picture over here, where if we're sort of thinking about which object a functor from a prop equips with algebraic structure, well, it's the object that's hit by 1. And more generally, the M is get to send to the nth power of that object that's hit by 1. So this axiom here says that C, the particular object C, is equipped with the structure of a P via this functor S sub C. Second is sort of a bookkeeping condition. The strong eta, so these are the coherence maps for the monoidal functor. If you work strictly, which you might think strictly, and if you're thinking strictly, you can avoid just saying this stuff at all. But because we're working with just a symmetric monoidal category C, not a strict symmetric monoidal category, I'm going to include this condition.
Is there a reason for that?
Not every symmetric monoidal category is strict. So sometimes I might want to honestly work with the category sets or something. And so it's good to have theory that works. But the point is, I mean, as you know, you take any symmetric monoidal category, and McLean says you can strictify it and work with a strict version of it. And this sort of stuff is coherent with respect to that construction.
Okay.
So,
I mean, you'd strict up there, so I'm just wondering why.
yeah, for some reason, props should be strict. Like the notion of algebraic theory seems to me to want to be strict.
No argument.
I guess because it's so syntactic. Like somehow you want to give yourself, you want to be able to constrain your syntactic side so that things are rigid and you can define things easily. But your semantic side, where you're working, you want to be sort of fairly agnostic about how sort of precise it wants to be, so you can actually have a lot of nice examples to work in. So it's sort of strict on this side, but not strict on this side. Okay, so we've said that we're equipping each object C with the structure of a P, and the last condition is this compatibility with a tensor product, which is sort of indicated by this sort of thing in the preamble. And when you abstract that away, I should have added some quantifiers really. So of course you know that M and N here are natural numbers, and C is an object of C, D is also an object of C, and I want to sort of take mu as a map from C to D in P. Sorry, M to N in D. In P. Okay. So if I have this stuff, then I want some squares to commute. So if I have some object, if I have an object C, I get a map from this functor S sub C, when applied to mu, gives me a map from C to the nth tensor power to C to the nth tensor power. So I get this map from here to C to the nth tensor power called S sub C of mu. I also get one for D, so I get a map called S sub D of mu from D to the nth tensor power to D to the nth tensor power, and here I'm just taking the tensor product of these two maps. So it's essentially this thing. I'm putting the map in parallel for two different objects. Except I'm putting them in parallel, and then I need to braid. Right? This goes to an object. Okay, let me say.
So if there m would be 1 and n would be 2?
Yes. In that example, m is 1 and n is 2. Okay. So I'm comparing the individual maps with the analogous map on the product C tensor D. So on C tensor D, I get a map called S sub C tensor D of mu from C tensor D to the m, so it's 1 over there, to C tensor D to the n. So that's 2 over there, which is why it has this sort of splitting picture over there. So that's all very well. And I want to compare these two things to make sure they cohere appropriately. And the point is that they're canonical, given just the ambient structure of the category C, there are canonical ways to take sort of m copies of C, then n copies of D, and turn it to n copies of C times D. Let me draw a picture. So, what do I mean by these sigmas? Well, the point is that I start off with a lot of copies of C and a lot of copies of D, and I want to end up with a lot of copies of CD. So there's one canonical way for us to do this, given by the structure of the category, and that's just sort of braiding things. So here's my first copy of C, here's my first copy of C goes to my first copy of C, second copy of C goes to my second copy of C, and last copy of C goes to my last copy of C, and similarly for the copies of D. So that's what these sigma maps look like. So you'll note that this sort of braiding here is an example of a sigma map where I started with A, B, B, and I went to A, B, A, B. So that's the one condition, and then there's, as in all these things, there's a binary condition and a nullary condition, just like there's a unit and a multiplication. So the nullary condition states that I have this map called S sub I of mu, which goes from I to the mth power to I to the nth power, and then I have some coherence mass in my category that do this. I'm writing calling them sigma, and this square should commute. Okay, so that's a definition of supply, which captures the idea that every object in my category is equipped with some algebraic structure in a way coherent with the tensor product. Now is a good time to get to examples, but I wanted to throw another. It seemed to work out better if I threw more definitions at you first. So apologies for one more definition. And that definition is this notion of sort of supply homomorphic with respect to supply, which I sort of gestured at the beginning. So